Welcome back to the Professors DuBois channel. I'm Professor Victoria and this is Professor Corey, and today we're going to be continuing on our thermochemistry discussions, and today we're going to talk about how energy is involved in phase changes.
And this is really one of my favorite slides in general chemistry. And what it is it's a graph, and I kind of like graphs, but if you look at this carefully, on the y-axis we have temperature in degrees Celsius, and on the x-axis we have heat added. So what does that mean? I'll try to explain. Let's make this real simple. Imagine you had this big block of ice, and you froze a thermometer right into the ice, and you stored it. You had a really nice freezer. It went down to -20. Okay, and these exist, -20 freezers. We have one, but we have one at the university. So we're at -20 degrees C. Now, when we pull that out of the freezer, immediately the surroundings are so much warmer than -20 degrees C that heat is flowing into this pot, right? But I'm going to put it on the stove, and I'm going to turn the heat on medium, okay? Just bear with me. And I'm going to just start, I'm not even keeping track of time. I'm just adding heat, right? Medium. So as I add heat, the temperature is increasing. So I'm just making note, of the temperature. And then something really, really interesting happens. It starts to melt. And this is the melting point. And for water, it's at 0 degrees C, and you'll need to know that. So at 0 degrees C, suddenly it starts to melt, and even though I'm adding heat, the temperature is not changing. And you can see that in my graph. So I'm going to turn the heat up a little bit. Why isn't my temperature changing? I'm going to go up to like 7. So I've got my heat at 7. It's melting. Temperature's not changing. When it's all melted, totally liquid in the pot, the temperature will start to increase again. So it'll continue until we hit what we call the boiling point. Now, the boiling point for water is 100 degrees C. And so if we did have a scale, we could put that in there. Nice. 100 degrees C. Another interesting phenomena. Water starts to boil. Temperature stops changing. Okay, now you can try this yourself at home, right? You can put a pot of water on, and if you have a thermometer, give this a try if you're curious. It's really interesting. When that starts to boil, the temperature doesn't change. Now, you can take your heat and turn it to 11. It's not going to change until we get to the gas state. Now, we'd have to have a closed system to measure the temperature of that gas, but this is steam. When we got all the liquid water into the gas phase, into steam, the temperature would again increase. Now, this is why steam burns, or steam's very dangerous. Steam is very, very hot.
That's true. Hotter
than boiling water. So watch out for steam. So there it is. That's my favorite slide in Gen Chem.
Yeah. So what's really going on? These are temperature, right? We measure temperature. It's something that we can observe on the macroscopic scale. But what's happening on the nanoscale or the atomic scale? So when we have that solid block of ice, we have if I just kind of draw this, I have my ice in my nice repeating solid crystal here, and as I add energy, or once we take it out of the freezer, it starts to absorb energy. Those molecules are vibrating more and more and more and more. So as our molecules, we're measuring this, but what's really, that means that the kinetic energy is increasing, right? Temperature is average kinetic energy. Well, what's kinetic energy? Energy of movement. So our molecules are moving faster. And when it's a solid, all we can do is vibrate. So it's vibrating more and more and more. And eventually it has enough energy to break free of the crystal lattice. And then we end up with a liquid. So now we have a random, closely in contact molecules, but they have enough energy to move and flow and move around next to each other. So that was melting. But at the point when it starts to melt, it is just taking that energy and breaking free those bonds that are holding the crystal lattice together. So the temperature is not increasing. What's increasing is the potential energy. So we've broken free of that crystal lattice, and we've increased our potential energy instead of our kinetic energy, until all of those bonds are broken and we can move on to then the next phase. And once we have all liquid, we can increase our temperature again. So we can increase our kinetic energy, and then we increase to have the phase change, we increase our potential energy. Then we can increase our kinetic energy again and get to the next phase.
So the potential energy is related to the distance between the particles.
Yeah, energy of position.
Now, one thing you mentioned, like the crystal lattice, and the example I used was water. And so water is held together by what we call like intermolecular forces of attraction, as opposed to like a
chemical bond,
like a crystal lattice for like an ionic substance. But same principle. It's the distance between the particles that's where that energy is going. When we turn up that oven and the temperature is not changing, that energy is going into increasing potential energy at that point, or distance between the particles.
All right, so of course we can calculate it. If we can talk about it, we can calculate it. So now we've been talking about heat, and heat is our Q, and that's our energy unit. And we call melting fusion. We like to use fancy words. So heat of fusion, the amount of heat, or the Q that's required to melt something, is kind of this new, we've talked about enthalpy. Have we talked about enthalpy yet? Enthalpy is H. So the heat of fusion, or the change in energy to melt, is the same as the heat that's required, or the heat that's given off to freeze. So whatever energy it took to melt something is, if you go in the opposite direction, that would be the same amount of heat that you'd have to remove in order to freeze it. So we only usually provide you with one of those values, the heat of fusion. And if you need to go in the opposite direction and you're removing heat, it's just a different sign. Remember, we were talking about Q, positive Q and negative Q, and that negative sign and positive sign is just which direction is the heat flowing. Are we increasing in energy, or are we decreasing in energy? And it's the same. So heat of vaporization then represents the phase change between liquid and gas, and the heat of fusion is between solid and liquid. And there's no temperature change during this transformation. And your heat of fusion and your heat of vaporization are given in joules per gram or joules per mole, but there's no temperature unit there. Anything to add?
Nothing to add.
Okay.
Let's see an example.
Yeah, it's better.
So we have water, and we have the given values here. You won't have to memorize any of these values, although you'll probably get comfortable with water, just because we use it so often. So we have a value for that, the heat of fusion and the heat of vaporization. Again, no temperature, because these are phase changes and the temperature does not change. So we have an example here. It says calculate the energy required to convert 250 grams of water at 100 degrees C from liquid to gas. So the temperature is not changing, but we're going to go from the liquid state to the gas state at 100 degrees C for water. So we need to apply the heat of vaporization here, because we're going from liquid to gas. So that's important. And we also have to apply the mass. We have to factor in the amount we have here. So if we multiply the mass, the 250 grams, by that heat of vaporization, which is in joules per gram, you see the grams cancel and we're left with a heat value in joules. I'll do that real quick.
Okay.
I'm curious. 2256 times 250. I've got 564,000. So this would be a good application of using kilojoules. You know, we might represent this at 564 kilojoules.
All right.
Now look at this next part of the question. It says, what if we went from water at 0 degrees to ice at 0 degrees? So this is the phase change, what we're calling fusion, but we're going from from water to ice. So we're actually freezing, and that means that energy is being given off. So we're going to use the heat of fusion value, but we're going to give it the negative sign, just indicating the direction of the energy flow. So again, just Q equals the mass times that the heat of fusion with the negative value, 333 times 250, and I've got 83,250. Grams cancel, units are in joules.
83,250. Oh.
83,250.
All right.
Now what's of interest to me is the vaporization value is so much bigger than the fusion or the melting value.
Right? I am kind of crazy about my sig figs, so I added a little dot here, so we had 3, and I gave it to the 3 sig figs because we're 3 up here. All right, putting it together. So we've talked about how to calculate when something is changing temperature, when one substance is changing temperature, and that's Q equals mc delta T. That was a previous lecture. And now we've talked about what happens and how to calculate Q for a phase change. Now this question is saying calculate the energy. Energy means Q. Energy means joules or kilojoules. Okay, I want you to start thinking about that. And necessary to convert their 250 grams of liquid water. So we're starting at liquid. We know it's between 0 and 100. And we're going to start at 40 degrees to steam. So steam means I'm in the gas phase or the vapor phase, and it says it's steam, so it's all steam at 100 degrees Celsius. So what we want you to do is start drawing something called a heating and cooling curve, and we have a picture here that represents what we kind of showed you before, but we want you to draw this for every problem that you do so you can find your roadmap. So we put our melting point and we put our boiling point, and we know these 0 and 100 for water. You need to be able to do this. If it's not water, the melting point and or boiling point would be provided. So you put your starting point on your curve and you put your ending point on your curve. So since it's steam at 100 degrees, it's here. This would be all liquid at 100 degrees. I'm trying to write. This would be all liquid at 100 degrees. This is all gas at 100 degrees. This is all solid at 0 down here. I'm trying to write down here. This would be all solid. And this would be all liquid, both at 0 degrees. So we have 2 steps. We have 2 steps. We have to go warm our liquid and then we vaporize our liquid. So this will be Q equals mc delta T. And this is what we just learned, where we have our Q equals delta H times our amount. So let's look at this as an actual, this worked out. You got this?
So our total heat is the heat required to heat the water up until it started to vaporize. So from 40 degrees to 100. And then we had to add the energy used or the heat to vaporize. So we did the first step, the mc delta T. You can see that below. 250 grams, 4.184 is the C value for water. And that delta T was 60 degrees. That's 100 minus 40, the starting. So we got a value 6.28 times 10 to the 4th joules for that. The vaporization part, we use the heat of vaporization times the mass, and we get 5.64 times 10 to the 5th. If we add these two together, we get the total heat.
Excellent. Here's a practice problem for you. Give it a try.
Pause the video and make sure you draw that heating curve to see how many steps you'll need to do to solve this problem.
All right, here's your answer. And in fact, you have 3 steps. So you have to melt the water, then heat the water, and then vaporize the water. And you're going to add all of these together. And this really walks you through. You have your 3 pieces here. And this is your final where you added all 3 of those pieces together. Hope you enjoyed that lecture and come back again.
Thanks for watching.
Keep talking about thermochemistry. Bye-bye.